Right. Arnab, you're live.
Yes, we are live. Good morning and welcome to yet another online session of Chai and Why. Actually, there is good news. It looks like that, Chai and Why started on the 4th of January 2009, and come January 2021, we should be back again at Prithvi Theatre and hopefully very soon at our other physical venues. Because, at the end of the day, we love to interact with all of you. It's nice to see you on screen, but it's so much better to see you in person and interact. Of course, we will continue to be in online. We've seen that online allows us to reach out to so many people across the world and also have speakers like today. We have our speaker who is in Kolkata. Anyway, coming back to our topic, November is the month where we look at the Nobel Prizes for the year. And just to remind you, we're going to have sessions on every Sunday of November. And today we're going to have Saranyo tell us about the first part of the Physics Nobel Prize. And Saranyo is a PhD student at TIFR. These talks are given exclusively by our students. And he is in the Department of Theoretical Physics. He works on problems, what happens when you have large number of particles, when they come together, what kind of phenomena emerges from that. And in particular, how does it affect things like entanglement and how do quantum effects develop, things like this. But today, of course, he has been very nice and volunteered to talk about the Nobel Prize this year, one part of it, the theoretical part of it. So over to you, Saranyo, and I will then switch off my video, mute myself. And just a reminder, if you're watching us on YouTube, please type in your questions in the chat box. If you're watching us on Facebook Live, please put it in the comments, and we will take the questions as they come. Remember, today's talk is a talk mainly on theoretical physics, so there's going to be a lot of concepts that we're going to go through. If something is not clear, please do shout. Saranyo has agreed to explain, whatever it is. We'll try and get things across. So with that, let's get started. Over to you, Saranyo. And okay. I hope things are good in Kolkata with COVID.
Yeah, nice. People are, they're fine. Yeah. Okay, thanks Arnab for the introduction. I'll be talking about, my talk today is called The Road to Singularity. We are going to talk about the Nobel Physics Prize of this year's, which was awarded to Sir Roger Penrose and Reinhard Genzel and Andrea Ghez. So it was split. Half of it was awarded to Roger Penrose, half of it to Reinhard Genzel and Andrea Ghez. The citations read for Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. And for Reinhard Genzel and Andrea Ghez, who shared the other half, it's for the discovery of a supermassive compact object at the center of our galaxy. More on this from Lankeshwar on the 29th of November. I hope you tune in and see the rest of the story as well. Today, we'll only be talking about Roger Penrose's contribution. So some of you may already know or have heard of the name of Roger Penrose from this book called The Road to Reality, where the title of my talk is also sort of fun on this. And it's a very nice book. I would encourage you to try and read it. It's an encyclopedic book if you would like. So moving on, the plan of the talk is going to be like this. We are trying to talk about what Roger Penrose did, but we're going to work up to that by talking about the basic ingredients on which all of his theory was built up on, as much as possible. Of course, I do not attempt, neither do I say that I can actually present each and every minute detail, neither do I know each and every minute detail, but I'll try my best to come across or present a complete picture as much as possible. Well, not complete, but at least an understandable picture as much as possible. So in the process, I might give not enough due credit to all the actors in the entire story. Neither may I do a very good job at explaining technical details. So people who are more knowledgeable than me, please excuse me on that part. So before diving into the rest of it, I just want to flash the paper which Roger Penrose published in 1965, which sparked off everything in this field. And as you can see over here, it's just a minute 3-page paper. And effectively, the things that transpired after this thing's publication in 1965 led to Roger Penrose winning the Nobel Prize this year. Moving on. So every road has a beginning, and our road begins at Newton's laws of gravitation, which is from 1687. So Isaac Newton basically said that if I have two massive bodies, one of mass m and the other of mass small m, and if the distance between them is small r, the force between them is basically given by this. It's an inverse square force, which basically means that the shorter I make the distance, the force keeps growing up. This is just the magnitude of the force. And the force is always attractive. That's why if you look at these arrows, which are a representative of the force, they always point towards each other. Along with the force, you can also define something called a potential energy, which also is inverse of the power, not square, which basically means that bodies which are further away are at higher potential. In a way, you could think of it as the further away you are, or think of yourself sitting over here. The higher up you are, the more potential that you have of getting hurt if you fall down. So in a more colloquial sense, you can think of it that way. So there's a potential energy. Now you can think of something called an escape velocity. You can think of, okay, same example, I'm sitting somewhere on the ground, and if I throw up a ball, and it can come down, it always does come down. But can there be a situation where I throw it up with enough kinetic energy such that it escapes gravitation? Remember, this force law basically tells me that if I go further and further out, the force is going to go to zero. So at some point, very far away, infinitely far away, I don't have any gravitation left. So what I start with is something like a planet of mass r and radius, mass m and radius r, and I have an object on the surface of it, and I throw it outwards with some velocity v escape. If the velocity is enough for it to reach an infinitely far point where both the kinetic and the potential energy is zero, I can just work the math that says that the total energy has to be conserved in this process and gives me an idea of what is the escape velocity, which is over here. You can calculate this for the Earth, and it turns out to be 11 kilometers per second. As a connection with what you probably have seen or heard of, every rocket, every satellite that we launch from the surface of the Earth has to have a velocity of this order of magnitude. Maybe not exactly this, something more than this maybe, but of this order of magnitude. Not meters per second, not something like that, kilometers per second. Now, in around 1784 or 1795, two people independently, John Mitchell and Pierre Simon Laplace, came up with this thought experiment that what if I have a star so compact and so dense that not even light can escape it, meaning that this escape velocity becomes greater than the speed of light. And if that is the case, even light can come out come out from the gravity of the star. And this gives you a relationship between the radius and the mass of the star. And they call this situation to be a dark star, meaning that no light coming out from it can actually come out or reach an observer at large distances. So if I take a star which has the mass of the sun, this critical radius R0 turns out to be 3 kilometers, just 3 kilometers. If you look at the actual radius of the sun, it is actually 7 lakh kilometers. So you can imagine how dense is going to be a star as large as the sun compressed into something like 3 kilometers, which you could probably get a Swiggy delivery from. And this tells you that this is an extremely high density, like 10 to the power 13 grams per cc. Just as something to compare with, the density of Earth is just 5 grams per cc. And this is 10 to the power 13. If I start writing zeros, it would end up somewhere over here. All of the zeros will end up somewhere over here. So it tells you that this is extremely dense, impossibly dense. And at that point of time in 1784 or 1795, people just considered this to be an impossibility and just a theoretical curiosity. And they just dropped it over there. And and that's the first precursor to something that we now colloquially know as a black hole, where even light cannot escape the gravity of such an object. Now, in hindsight, at such high densities, Newton's laws of gravitation are inaccurate. They should not be applied. They give you a wrong idea of what is happening. And they need to be replaced with Einstein's general theory of relativity, which came up in 1915. Remember, Newton's laws came up in 1687. They worked very well for almost 200 years. And only when people got to very high densities, very close to stars, and so on and so forth, people started thinking about general theory of relativity. And as you can see, what modern gravitation works with, or likes rather, is Einstein rather than good old Newtonian stuff. Now, what is the general theory of relativity? Is a theory of geometry of spacetime in the presence of matter, as a more colloquial way of presenting the theory. Now, what in the rest of the slides, I am going to unpack what this statement qualitatively means. So there are two ingredients over here. So there is space-time. There's one little concept or one little word that I've used, and then there's another thing, geometry. So now let us look at what is space-time. So think of having some sort of space. Think of looking at something like a movie where you have an object which is stationary over here, and as time progresses, this little bar, which could be a car or whatever, it just moves along a line like that. Now, you can basically think of the movie as a collection of images. So you can take each of the frames and stack them on top of each other. So you can take the picture that you're seeing now over here, the picture which will come 2 seconds after, you can place up top, the picture which came 2 seconds before, place below. Stack up all of these snapshots that you have taken at different points of time. And what you get, and follow how this, follow the position of this dot over here. Of course, this dot remains stationary. So over here, the dots on different slices basically align, and you get simply a line. Over here, the two things where this entire object, the car, was moving. So what you see over here is that these things look like they're bending. So you had space along these two axes and time along the vertical axis. This is what is called space-time. You take space and time together, colloquially. Let's do another example which will make this thing clearer. So let's take a cartoon of Earth rotating around the sun. Suppose it, so this is in the centerpiece, there's the sun, this little dot is the Earth, and as time goes on, it is rotating like, now, as time goes on, it's rotating like this, right? So in January, suppose it was here, in April, suppose it was here, in July, suppose it was here, in October, suppose it was here. So I have my different time points. I place them on top of each other, these snapshots. And then as a result of stacking, I will now get a space-time diagram showing that, okay, at January, it was over here. In the center, the sun always remains at the same place. So it will just create a line, which is the center line. And then when I actually thread together all of these things, I will basically see that in space-time, the motion of Earth around the sun basically looks like a helix that is moving up in space-time. So what we have done through this procedure is take motion in space, just space, and replace it by shapes in space-time. So over here, just to expound on that point again, I had motion in just space over here. I had something rotating. In space-time, that effectively becomes an entire shape, because now I'm looking at all possible times and all possible shape all together. So what we have effectively done is something central to this root of physics, or this branch of physics, is that you think of dynamics, instead of thinking only of dynamics, you think about geometry, where space and time are treated on the equal footing, and you think of objects in space-time. So moving on, you can ask, okay, fine, but what does light look like in space-time? What does it look like? Suppose you have an event where you had a star over here which exploded. So what is happening is there are pulses of light which are moving out in concentric circles. They're just radiating in every direction. So an explosion. On the other hand, you can consider the opposite process where there are concentric circles of light coming into a point. Think of them, if you're having difficulty with light, think of them with water waves, for example. You can have water waves, circular water waves converging to a point. You can have circular water waves coming out of a point. Now, what does it look like? What does this motion look like, or this motion look like in space-time? So look at it like here, the red dot that you're seeing is basically the light pulse going out. So over here, if you track it, each point gets displaced by time, and then it goes out again. So what it essentially creates looks something like a cone. So the motion of light generates, so these things in space-time are called light cones. Very imaginative naming sense, as you can see. So you have a cone of light, and then you might ask, okay, fine, but why do I care? So Einstein's
Sharana,
special theory of,
can you just repeat this light cone perhaps one more time? How did you
sure,
get two sides of the cone?
right. So the lower side of the cone corresponds to the implosion process. As you can see, when I'm going from down to up, this is the point. This is the point at in the middle. This point over here. You started from a point over here where the light now is coming in to the object. So as you can see, it's getting smaller and smaller. The radius is getting smaller and smaller. Once it reaches that object, light is now going out. So the radius becomes larger and larger, which is happening in the top half. So the top half, if you think this we will come to it in a moment as well. The top half is the explosion process, light going outwards. The bottom half is the implosion process where light is coming inwards. So in
Thanks.
space-time, yeah, great. So that's what the light cone is supposed to mean. Now, why do I care? So Einstein's special theory of relativity, not the general one, the special theory of relativity from 1905 postulates that the speed of light in vacuum is like a cosmic speed limit. What does that mean? It means that no process with a cause-effect relationship can involve speeds greater than the speed of light. What that means in other terms, it means that I cannot go beyond the speed of light and hope to influence anything else in physical reality. So C is the absolute maximum. You cannot go beyond that. So as a result, the light cones, they partition space-time around every point in three distinct regions. One is the future light cone, saying that if I'm at a point over here, it's all the points which are within this entire cone, which by the way extends to infinity and whatnot. But then we look at over here. So the point starting from here can go here, or go here, or go here, or go here. So all of these points are called the future. There's the past light cone, saying that what points could this O have come from, meaning that this point could reach over here, that point could reach over there, and all of these points could, in principle, reach this point O. And the third part is the everything that is remaining, so on the sides, which is called space-like separated. Remember, since the speed of light is the absolute maximum, there is no way for this point to have any effect, causal effect, on points in this region. There is, so to if I had to think of a hypothetical situation where I start at this point and I want to end up here, I would have to travel at speeds higher than the speed of light, and that is not possible. So there is no way. Yeah,
Sharana, there are a couple of questions on the YouTube chat
sure.
on this thing. Like, what exactly, Moksh wants to know, what exactly do you mean by the statement cause-effect relationship? And somebody else has exactly the same thing. Can you please explain cause-effect relationship? And does it mean that there are situations where you can go faster than the speed of light if you don't have this cause-effect relationship or whatever else?
Right. So You can always calculate. So let me answer the second one first. If you just calculate the velocity, there's like formulas that you get during high school and whatnot, that, oh, calculate the speed of a train which is going in this direction, traveled 50 kilometers in 5 hours. So the speed is distance divided by total time, which is 10 kilometers an hour. So you could always take that formula, blindly apply it, and in some cases you do end up with a value which is greater than the speed of light. But that actually doesn't mean that it's actually that you can transmit any information from one point to another using that value. So you can think of it in this way. People have done experiments or just back of the envelope calculations where they've shown a laser pointer on the surface of the moon, and they just flicker their wrists a little bit. And since the distance is so large, the other side, the endpoint, will actually move at a speed greater than the speed of light. The numerical value will be greater than the speed of light. And this is where cause-effect relationship becomes very important, where you basically are thinking of a situation where one event actually influences the other event. What I mean is, suppose I want to pick up, uh, suppose I have my phone. I want to open up my phone and I want to touch on its screen and it would light up, something like that. And I can see that it's lighting up and whatnot. So a cause effect relationship is the phone lighting up because I tapped on it. My tapping is the cause, the phone lighting up is the effect. Now, what I'm saying is that this kind of a process where there is a definite cause influencing something happening later cannot happen at speeds greater than the speed of light. I cannot tap this at 3 into 10 to the power 9 meter per second. I physically, of course, can tap it even larger than whatever, 3 centimeters per second maybe. But there is no way that I could even build a machine which is fast enough and do all that. It is not possible, simply not possible. So if I were to look at timings, and I were to find that this thing is happening at speeds faster than what is predicted by this cosmic speed limit, you would probably figure out that, okay, there is something weird happening, or you get all sorts of weirdnesses in the theory. So for the moment, this is what I mean by cause effect relationship. If I move or if some operation or some action is happening at speeds greater than the speed of light, it cannot influence other things. That's what I'm trying to say. Is that clear? Or maybe I move on? Yeah, sure. Okay.
Go ahead.
So,
and I mean, so the light cones are always conical. I mean, whatever is outside these two cones is in a region which sort of is not possible. I mean, nothing could have come.
It's not reachable. So
not reachable. Okay.
They're not reachable. So within the theory of special theory of relativity, you can always have points over here, but they are not going to be influenced by whatever is sitting at this point. So you can think of the future cone as whatever things this point can influence, the past cone as the possible events that could have influenced this point, and everything else is things beyond the scope of influence. Let's put it that way. So let's move on.
Yeah.
This point that I picked up is nothing special. I could have taken up any point in all of space-time, and each point I could have just constructed a light cone. So again, time is flowing in this direction, space is in this direction. I've suppressed two more directions of space just so that it's easier to imagine. So these horizontal dotted lines are at equal values of time. So at one value of time, at different value of space, I can always construct these light cones. They're just cones. And now, what do paths look like? I mean, I start at this point, and all I'm saying is that I can have a path like this, like that, like this, like that, like that. So let me go forward. Suppose I want a path which at this point of time was here, second point of time was over here, third point of time was here, fourth point of time was here. All that I'm saying is a possible path looks like this, meaning that if it has to start from this point, this red line has to remain within this circle, within this cone. And if it has to reach this point, it has to be within this one, this cone, which is the past light cone of this point. Then again, if it has to move away from this guy, it has to remain within that. So it's always within the light cone. There is no way for it to go outside the thing if it wants to reach these particular points at those particular times. This is a constraint on the possible paths that you can have between two or more points in space-time. So let's look at another path. So now I say that, okay, I start from the same point, but I want to go here. Then I want to end up here. Then I want to go there. So if I want to end up here, I cannot go here and then over there. That is not possible in the theory. Because if I want to do that, I have to go outside of light cones and violate special theory of relativity. So a path can be like this. Remember, if I just said that, okay, I want to go from this point to that point, this is a valid path. That is also a valid path. I could have come up with, maybe I sketch a certain thing. I could have come up with another path, which is like this, which is also possible because it goes through that point. There are intermediate points at which you will have light cones over here and light cones over there, but it's always possible to reach. There are many paths which can take it from here to here, but you cannot have arbitrary paths. That is the entire point. So now remember, you don't need actual light to construct light cones. You just put a cone at every point. So the future of point P, as I was saying, represents the range of possibilities that a trajectory can subsequently take. So this effectively, this part, if I start from this point over here, this part represents all the kind of places I could have gone, whereas the past represents all the places I could have come from. All that it's saying, the light cone structure is basically saying that if I'm at this point, I could not have come from this point over here. That's all that it's saying. So that is the space-like separated part. So you don't actually need light to form light cones. It is motivated from light, sure. But then you just are looking at what are the range of possibilities of future motion and what are the range of possibilities of precursors. That's the past and the future. This is a definition that we'll be working with over and over again. Now, if there are further questions on space-time or light cones, this is the point for people to ask. So go ahead. None. Okay, I move on. So geometry. Let's move on to geometry. So people have always seen the world map in textbooks and whatnot, but the world closer to reality looks like this, where you have latitudes, which are the horizontal lines on this projection, and then you have the longitudes, which are the vertical curved lines over here, or the curved lines over here. Let me use the pointer. So the vertical lines over here, which are the longitudes. Now you can ask that, okay, fine. When I want to look at geometry, there are two things that I want to ask. I want to ask what is the distance between 2 points, which is the metric. And I want to ask, okay, but given 2 points, suppose a point over here, suppose a point over here and a point over here, what is the minimum distance that I need to go to join these 2 points? And that is answered by the geodesic. So there are two concepts over here. One is the metric, the other is the geodesic. So let's dive into the metric right now. So let's look at two-dimensional space. There is X. Let me use a pen. There's X and there's Y. And there's some angle. Let's call it theta for notational convenience. Fine. So at this point, the coordinates of this point is just X and Y. And what is the distance between the origin, which is 0, 0, to X and Y? Usual Pythagoras, right? So all it says is that this distance is Y and this distance is X, right? So Pythagoras basically tells me that hypotenuse square is basically X square plus Y square, but then I could have done a separate object. I could have worked in these coordinates of R cos theta and R sin theta. So if I'm at this point, which is suppose X, Y, and this point, which is X plus dx and Y plus dy, I'm now looking at 2 points which are separated by a small amount, d theta. So what I want is this distance between them, the point connecting A and B. So this red line is what I want. Now, I can effectively find it from coordinate geometry. If this distance is basically dr, then dr square from Pythagoras again, because I can construct a triangle like this, which tells me that the x displacement is that much and the y displacement is that much. You get dx squared plus dy squared. Or I can consider this triangle over here. Maybe I do a better job of drawing. So I construct this triangle over here, where now I want to find what is this distance and what is this distance. This, as you can imagine, is just a change in the radius. So it's a dr. And this is a change in the angle. So I can, when this angle d theta is very small, I can approximate this length by the length of the arc AB. So I write, so this was O or P, whatever. I can write PB is approximately AB, and this AB is equal to R d theta. And again, I now, if I want to find the distance like this, I use Pythagoras again. So I get that this object, so let me call it this ds square, which is the distance, that is given by dr square, which is the change in the radius, and then this pb square, which I now approximated as r d theta. So I get r square d theta square. So all that has changed, and these two things are the same, mind you. These two expressions are the same. They're just in different coordinates. In one coordinate system, I had chosen x, y, which is the Cartesian coordinates. And the other system, I had chosen r and theta, which are the polar coordinates. So all it's telling you is a general form of what the little infinitesimal distance looks like. You choose your coordinates, but then when you add them up, you need to scale by certain things, right? In the Cartesian one, all the scaling factors were just 1. I don't know why this is happening, but let's see. All the scaling factors were just 1. In the polar system, one of the scaling factors was 1. The other scaling factor was r squared. I could now have some situation where I could have dr squared plus dr d theta as well, with some scaling factor over here. Again, some scaling factor here, d theta squared. This is also possible if I choose some other weird sense of coordinates. So in general, the metric decides how to find distances between 2 points. And a general form of that is gij dxi dxj, sum over I and j. So if I and j are 1 and 2 up to 2, then what I'm saying is g11 dx1 square plus g22 dx2 square, g12 dx1 dx2 plus g21 dx2 dx1. So as you can see, if I just compare this form with what I had over here, if I chose my x1 as x and y as x2 as y, then I only have g11 and g22. G12 and G21 are 0. So the metric is essentially G, I, J. Or later on, what we'll see, G mu nu. Mu nu's are also coordinates, indices of the coordinates. And then this is an abstract way of writing down distances. If I give you what G mu nu is, I have told you how to compute distances in any given metric. So this is one of the things that classifies a geometry, the metric. And then there's the idea of geodesics. Now I have a way of computing distances, but what is the shortest distance? So going back to the globe, Suppose I had point A and I had point B, you could have thought that the shortest distance is just connect them across the graph, right? So you go along the latitude. Turns out that this is not the case. The actual shortest distance is the great circle passing through the points A and B. What I mean by a great circle, so longitudes effectively are also great circles. A great circle is something which intersects the plane which contains this circle, intersects the sphere and passes through the origin. So I could have a great circle like this. I could have a great circle like that. All of these are great circles. But this, if I put something like that, it doesn't pass through the center and it's not a great circle, right? So you can find that this is not something that I'm just selling to you. People actually use this. So you can look at flight paths over the globe from say Madrid to New York. And what you see over here that you might think that it's along the latitude, but actual flight paths are along a great circle like that. It's even better pronounced when you go from say Dubai to somewhere, I guess this is Chicago. You won't fly like this along the latitude. You actually fly closer to the North Pole. You fly over Greenland, in fact, because it's the Great Circle. So a geodesic, this is the concept that we are defining. So all of these great circles are geodesics. Geodesics are the shortest path between 2 points. And the study of these things are important to classify what kind of geometry we have. So the metric is important, and then the geodesic is important. And the reason why the shortest distance was not the straight line, as we would think in regular space, in regular experience, is because that the space has some intrinsic curvature. So this is where you first find yourself looking at this thing called curvature of space or curvature of some geometry, and which influences how geodesics behave, which influences how the metric behaves. And this is the idea that Einstein actually built up on. So Einstein's basic general theory of relativity, I'll just give you the punchline here. It's too complicated and we're short on time to talk about. This can be an entire talk or a course by itself, to be honest. So the punchline is that you have energy and matter, and that influences the curvature of space-time. Remember, space-time is just some kind of geometry that I'm looking at, and that has some intrinsic curvature as well. So energy and matter, it influences curvature. And then the second part of it is that the curvature of space-time influence the motion of other matter moving around. And these are sort of the equations for general relativity. I've dropped out the cosmological constant because I don't want to go into that. So so what do these things mean? These mu and nu are indices. They can go from 0, 1, 2, 3. Typically 0 is reserved for the time coordinate. 1, 2, and 3 represent the space coordinates in space-time. And then this basically gives you a set of 11 independent equations. They are coupled, they're nonlinear, and they are partial differential equations for the metric components g mu nu. So what you're doing is providing, first, T mu nu. What is T mu nu? It is the energy and matter that I talked about over here. So T mu nu is the energy and matter. It basically tells you what is, say, the pressure, what is the density of mass, what is the energy. It also includes shearing effects. So if I have something and like push one side where pull the other side, it produces shear. It also has currents and whatever you can think of. So all the energy and matter is over here. Remember, Einstein's equations are a cause-effect relationship, meaning that you supply a T mu nu, you supply a distribution of energy and matter, and that you use as an input to calculate G mu nu. So it's cause-effect. So that's sort of the framework of GTR. But the question is, but do these equations predict singularities? The answer came very soon after General Theory of Relativity, which is sometime in 1915. I think, I don't remember the month, but somewhere in the middle of the year. And within a month or 2 months, the Schwarzschild solution came up. So Karl Schwarzschild came up with a solution of this beast over here in the situation where he considered T mu nu equal to 0. He found a solution. So he assumed spherical symmetry. What he's looking at is basically a star like that, and he's looking for the gravitation at a point outside. So G mu nu equal to what? This is what he's trying to find. He assumes spherical symmetry, meaning that if I were to look at this direction in the star versus that direction in the star, it should be the same. So he's considered a situation where there's nothing except this star at the center. So all directions are the same. I can just rotate it and it'll be fine. So my coordinates are t, r, theta, and phi. R and theta you just saw. Phi is another angle in spherical polar coordinates. And this is what he finds for the metric components. Remember that there is a typical length scale over here called the Schwarzschild radius. And turns out, maybe surprisingly, maybe not surprisingly, that this is equal to the radius that our good old friends Mitchell and Laplace had found out about from the discussion on dark stars. But then what is the content of this equation? I'm just showing you equations. Why do you care about equations? Remember what these G's were. They were scaling factors, right? So,
Saranyo, by chance, have you touched your mic? It's just crackling suddenly.
I shouldn't have, but is it still crackling?
A little, yes. I don't know why. It just suddenly started crackling. I hope the network connectivity is good for you. Okay, just keep going. Keep going. We can't help.
Yeah, I mean, okay. Let's hope. Otherwise, I try to do something. So So remember, all these G's were just scaling factors. So if I were to look at distances,
if I were to use your computer mic, would it be better?
I'm not sure, but I will change and we can test. And that is, are you having a better sound now?
Much better. I think so.
Okay, fine.
Audience, is this better?
I mean, it's hard to get live feedbacks.
Can someone please post on YouTube if somebody posted about the disturbance. Why don't you continue? I think this is a better, I think at least we can hear you better. Sure.
I'm fine to continue with this.
Yeah, go ahead. I think this is much better.
Okay, great. So, so what we're now going to look at, remember, so the metric effectively had a GTT, dt square, plus a GRR, dr square, plus some angular parts, which I'm not writing at the moment. It's the r and the theta part. Remember, this GTT is effectively the scaling of time. It tells you how much you need to stretch or contract your value of time to make sense. So what this actually tells you is this incredible fact that if you actually take a star like, if you actually take a star like this, so this is a star of radius r with some mass, and this dotted line over here is the Schwarzschild radius. This is Rs. If you take clocks at different points, at different distances from the star, the clocks actually start running faster. If you take the clocks outward, it runs faster. And if you want the actual formula, it is basically given by this. And as I told you, the stretch times, these are the stretching times. So square roots of GTT is the actual stretch. GTT is square of the scaling or the stretching. And this gives you a relation between what is the time difference if I were to measure it at a position R1, suppose over here, versus R2 over here. And they will be stretched. So you can think, okay, but is this just something I cooked up, or is it something that I can measure? So think of, what if this star was the Earth? Suppose, not a star, maybe any planet will also work. So suppose this object is the Earth, and I can calculate what it is. So I can measure the time at different altitudes on Earth. So if I go to an altitude of 2000 kilometers, the clocks actually turn out to run faster by 10 to the power minus 10 seconds. So you can figure out that it's a very, very, very small correction.
But turns out this is enough for GPS to function. And this is the guiding principle behind GPS working. So this is not all for shits and giggles. This actually has effects which people use and which people exploit to create something which is virtually with anybody with a smartphone at this moment. Right. So that's the Schwarzschild solution. Now we can ask what happens if the radius is smaller than the Schwarzschild one. In this case, the red thing was inside. This was the radius of the star, and the Schwarzschild radius was inside. You can ask what happens when the radius of the star is even smaller, meaning that it's more compact. Same mass, radius smaller. Same thing will happen. Time will run slower and whatnot. But what happens at the Schwarzschild radius? Remember, in the formula over here, you had this typical Rs sitting over here. So if I put R2 over here as Rs, this just cancels out. You get an infinity. So it means that if I measure an event over here, which lasted for 1 second, over here it will seem like it lasted for an infinity of seconds, meaning that the time difference between events goes to infinity, meaning that if I take a light pulse over here, the pulse never makes it out. It takes infinite amount of time to come from here to here. Or is another way of saying, so infinite time to reach the observer at larger R, which is equivalent to saying that light never escapes from this region, which essentially means that this is a black hole, as we have defined, that there is nothing that can escape this. And R equal to Rs is called the event horizon, which literally the naming, I guess, is because the fact that you can see all events which happen here, here, here. You can see means that light from here can actually reach your eyes. That's a very bad eye, but anyway, light from here can reach your eye over there, but light from this region over here cannot reach your eyes. So they are very redshifted and whatnot. Now, there's no comment about in Schwarzschild solution about how this situation can happen. I mean, how does a star become so compactified that it can actually work? And so many people at that point of time in 1915 thought that this is again just some math. There's no actual physical content in it. So this is the thing, that are these conditions of collapse actually even physically possible? So, and the answer came from Subramaniam Chandrasekhar at one point, who basically said that, look, there is actually a critical mass that stars can support. The stars are objects which are in constant turmoil. There's gravity, which is trying to crush the star into a point, and there's the radiation, which is actually inside, which is trying to push it outwards. So you have a star like this, suppose. Gravity is pulling inwards, radiation is pushing outwards. And it's always a balance of these two things. Now, once it has reached the end point, and this radiation comes from burning its internal fuel, which is hydrogen and then helium, and so on and so forth. But then there's a limit to how much a star can burn, and after a point, it can't burn anymore. So what happens is that it contracts, it creates something, and then it is held up by what is called degeneracy pressure, and that has a limit, which is 1.4 m solar masses, which is called a white dwarf star. This is Subramaniam Chandrasekhar's contribution. And then there were other people. So the point over here is that the star at that point is held up by the degeneracy pressure of electrons, which is a quantum effect. And then later on, you can have neutron stars, which are even smaller, but there's still a limit on that. I forgot what the limit is, which are going to be held up by the pressure, degeneracy pressure of neutrons. But you can have stars which are even larger, even more massive than that. What happens to those? So this is where in 1939, Oppenheimer and Schneider came out with this idea of continued gravitational contraction, which basically says, consider a star which is so massive that it cannot be supported by any of the degeneracy pressures. What happens then? And they showed that you can actually solve for it and figure out that it actually contracts and creates a singularity over here. But then they're talking about always a spherical distribution of dust. meaning that you still have this spherical symmetry, that if you look this direction, that direction, every direction is the same, right? By the way, Oppenheimer was also the guy who coordinated the Los Alamos, the project in Los Alamos, and I mean, if any of you have read Feynman's memoirs, or not really memoirs, this book called Surely You're Joking, Mr. Feynman, you can get mentions of Oppenheimer actually roping him in to do some stuff and whatnot. So yeah, so Oppenheimer has a part in the history of the current world as well. Right, so the point that you have over here is, at that point people show that okay, the math works out, but they believe that in a realistic situation nothing is going to be spherically symmetric. Things are going to rotate, things are going to shear, they're going to do all sorts of things, and this would prevent the collapse from happening. So, and this is where we now come to the Indian connection of the Nobel Prize of this year's, which is the contribution of Professor Amul Kumar Rai Chaudhary. So think of a bundle of world lines. What I didn't mention to you was that in space-time, when I take the point which is going like that or that, this is called a whirl line of the particle, right? So it's basically that in loose sense, it's the trajectory. It's not actually, trajectories are only in space. The curves that that come out in space-time are called whirl lines. Now, suppose you take a bunch of whirl lines, which are conveniently expressed over here by a bunch of spaghetti. So you start from this point, they're not intersecting, and what can happen to them as they go upwards through space-time? They can expand, meaning that if I look at the area, suppose over here where the string is, I look at how much they have pushed up, this area can expand, this area can stay the same, or it can actually shift around, it can rotate, it can shear, keeping the volume same, but changing shape. So if I were to look at this picture from the top, so if I look at this thing over here, I'm going to see whirl lines like that. Earlier, they were just points like this, regular points. Now I can see that they have actually twisted around or something. So what governs these kind of features? Like, are they just always going to expand? Are they always going to shear? Are they not going to do any of these things? What happens to the possibilities? This is where Amul Kumar Rai Chaudhary comes in, an Indian astrophysicist, theoretical physicist who lived and worked in Kolkata for most of his life. And he gave, incidentally, he gave one of the first not extensions, but first progresses to General Theory of Relativity in 1955, almost a few months after Einstein died. So it's a bit unfortunate that the timing didn't match. So same idea, we are considering a bunch of these timelines, a bunch of these whirl lines. So particle whirl lines, they are sometimes called time-like, meaning that they're within the cone at every point. They're always within the cone. They're not outside of it. That's what time-like means. And they don't intersect at a point of time, by which I mean this point of time. I don't have a point where two spaghetti things actually intersect. So, and the Rai-Chaudhary equation in that situation states that, well, basically states this, where theta is basically, it's called the expansion factor, and it looks at the expansion of and contraction of A. Suppose this is the cross-sectional area, A. It looks at the expansion or contraction of this locally, meaning that at every point, lambda is kind of like the time. So if you look at different points of time, A can become something like this, or A can become something like that. So at different points of time, this is say A1 or A2. So theta basically looks at, for a small change in lambda, what happens to A. And as I was showing you, A can become larger. So theta is positive in this situation. Theta is 0 in this situation. And if it becomes smaller, theta is negative. So contractions are negative, expansions are positive. And then this tells you, this equation over here tells you what happens to the rate of change of this expansion or contraction. So you have your contraction factor over here. The R mu nu, U mu, U nu is basically, so there are sums over here everywhere, U mu, mu nu. So this entire thing is a contribution from the matter or energy which was present. Remember, we're talking about space-time in response to some matter. So there has to be some matter content. So there is something called the strong energy condition, which says that this energy contribution is positive. So this guy is positive. This guy only is positive. So, and that's not a very weird thing to ask. It's all true for all forms of ordinary matter that we know. So if this is positive, this you can show is always positive. This is effectively something like sigma square. So it's always positive. You can show that theta dot is always negative. It's always bounded like that. You can shift things around, do a bit of integration, and show that this condition is equivalent to this condition. Now, what does that mean? What does that mean? If I were to have a theta zero is the initial contraction or initial state of expansion or whatever. If it was initially contracting, meaning that I start from a situation like this and it's initially going to something smaller. If this was the thing at initial times, then it basically says that theta is negative at all times, meaning that if at the start it was contracting, it will always remain contracting. And under certain situations, this can actually lead to something called focusing as well. So if this thing was equal, if 1 over theta was equal to 1 over theta 0 plus lambda over 3, at a particular time of lambda equal to minus 3 by theta 0, which is finite, this would turn out to be 0. So if 1 over theta is 0, I know theta is equal, theta goes to infinity, which essentially means that the area has now shrunk infinitely. The area has shrunk infinitely. Thank you. Sorry. So the area effectively shrinks to a point, and there's a focal point now with infinite density. So, which is a singularity. So, in essence, this theory was the first instance of a singularity theorem, and it turns out to be the basis of all singularity theorems that were proved after this. Of course, there were more inputs and all sorts of important concepts, but then this is also a very key ingredient. You cannot talk of singularity theorems without using what Amal Kumar Rajchandri actually penned down in 1955. So the takeaway from this thing is that there is some essence. So what the Rajchandri equation predicts is that if you have space on which trajectories are going like that, they will all focus to a point like this. So there is a focal point somewhere. Everything is contracting. But then you might ask that, okay, this is a talk about singularities, and I just showed you that there is a focal point. Are we done? Then where does Roger Penrose even come in? But so let's be a bit more precise. What I showed you over here rigorously, I showed you when this thing was equal. What I actually find from the equation is this thing is greater than equal, not exactly equal. So in particular situations, when it is actually equal, you can show that fine, okay, it contracts to a point and there is a physical singularity. In general, that is not the case. In general, all you know is that it is contracting. That's all. You don't know whether it goes to a point or multiple points. So what can happen is that the lines can actually lead to what is called a caustic. A caustic is something that you actually seen all the time in your life. Suppose you have like a glass of water and sunlight passes through it. What happens is different rays, they come together, they don't meet at one point, but they all of them effectively trace out a surface which becomes very, 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 very bright. So these are all caustic surfaces. So as you can see over here, different lights coming from different points, they reflect, refract, do all sorts of things. This is the focal point, but all the light basically is bound to a small volume around the focal point, not at the focal point. So you might ask that, fine, I mean, AKR proved it for material particles, and there is some physical singularity. If I had some matter in a point and I squish it to just a point, the density over here goes to infinity, right? So there's a physical singularity. But what happens to space-time itself? What about light cones? So how do they move? So what is this? Is there something called singular space-time itself? Not material particles, space-time itself. Turns out that this is quite a tricky question. In typical sense, a singularity essentially means something which is diverging, like over here, where I had the density, the physical density going to infinity, or maybe since we're talking about geometry, you can think of the curvature going to infinity. But then the Einstein equations, when we wrote them down, the implicit assumption that went into it was that at every point of time, the curvature was well defined and it's regular. So I had an equation where I'm now saying that no, it's not, it's actually infinity, makes it a bit shady if you want. So it's a bit tricky of how you would try to push for singularities. So the resolution came from an algebraic geometer called Roger Penrose, and I guess this is when he was younger. And the resolution he proposed was to follow curves in spacetime. Instead of looking at the curvature itself, follow curves. What do curves do? And he defined a notion of singular spacetimes as to be the fact that if a spacetime is singular, if curves start or end abruptly, meaning that they cannot be extended endlessly beyond a point. Remember how we constructed spacetime. We were taking pictures of something and then stacking pictures. So I could have taken pictures till the end of time, or from the beginning of time till the end of time, and it would have gone up and up and up. So I could go up this time axis as much as I want. But then suppose I had a situation where it just started from some particular point in time. So if this happens, if there is no way of removing this situation, or it goes up to a point and just ends somewhere, there is no point of following this curve even further, that is called, if such a situation happened, then it's a singularity. The space-time has a singularity. And to
Sharanya, just to remind you that on your time curve, you are at about an hour right now.
Yeah,
and
exactly.
You also do not have infinite time.
That's true, and I'll also be finishing in 5 minutes from now.
Okay.
So, well, I mean, since I took questions in between, I hope you'll be a bit lax about questions.
Yeah. No problem. It's going really well. So keep going.
So the two concepts that he introduced at this point were these things over here in red. One is called geodesic incompleteness. The other thing is called closed trap surfaces, and we'll get to it in a point. But before that, let's talk about Penrose a slight bit. So as I said, Penrose was a geometry guy. He was an algebraic geometrist. I don't know what the word is, geometer, I guess, algebraic geometer, who basically was doing math at that point of time, essentially math. And it's no surprise that he started proving theorems about the geometry of space-time, or the topology, in this case, actually the topology of space-time, because he has done these things before as well. So look at this picture over here, which is called the impossible tribar. This is something that Penrose actually got, which is actually found by Oscar Reuterswald in 1934, or the impossible staircase in 1937. As you can easily imagine, or maybe not easily imagine, that if I say that this thing was the inside of this thing and I start going around, I effectively turn out to be on the outside of what I would perceive to be the image. And then if I keep going, I basically go down, and then I can come up on the other side and keep on going. So it's very weird. At some point when I come back, I don't have any idea of whether it's up or down anymore. Or in fact, it turns out that this stereographic projection that people have drawn is impossible to create in 3D reality. It's impossible, simply. So that's why it's called the impossible tribar. It's also called the Penrose triangle. So these things were found or built by Oscar Reuterswald, but then popularized by Roger Penrose and his father, Lionel Penrose, in the 1950s. And this actually ended up inspiring another great of this kind of pictures, impossible pictures, called M.C. Escher, the Dutch lithographer, who actually took inspiration from the impossible staircase to make this very famous picture called Ascending and Descending. So if you actually take a look at the picture, there's no way of telling whether at each point the person is going up or going down. This guy is going up, this guy is going down, but then there is no way of assigning this height to be larger than this guy's height. So you'll always have a contradiction somewhere. If you say that if this is going up, this is higher than this side. If it's going up, this is higher than this side. Going up, this is higher than this side. Still going up, so this should be higher than this side. But then by contradiction, these two have to be the same. So there is some contradiction over here. These two cannot be the same. So, and then another Escher painting, because this is one of the things that I saw for the first time, one of the first Escher paintings I saw is Relativity, where you see that there are like staircases going in all direction and all ways and people coming out. So there's no way of finding out which way gravity acts. So Penrose had an effect in a way outside of physics and geometry and all sorts of cool things like this. He also had an effect in finding out aperiodic tessellations, which are called Penrose tilings. Aperiodic basically means that if I take this picture over here, if I take it just by itself and just shift it, translate it by an amount, it will never fit on itself. If I just translate, it will never fit on itself. For example, in contrast, if I take something like a square lattice like that, if I shift it by, if this gets shifted to here, it will be the exact same lattice again. It will just match on top of each other if just shifted by a particular amount. In this case, it is never possible. That's why it's aperiodic. So people might think that this is actually just fanciful math, but it actually happens in nature as well. This particular one has five-fold symmetry, which I don't have time to explain at the moment. But so Dan Shetman actually found icosahedral quasi-crystal in 1982, which actually has, if you count the number of points around the central spot, there are 10 of them, which show that it has five-fold symmetry, and that won Dan Shetman the Nobel laureate, the Nobel Prize in chemistry in 2011. Of course, Penrose didn't particularly contribute to this finding, but there is a link in some sense. So Penrose has done multiple things. But then coming back to what we were trying to talk about. So geodesic incompleteness and closed trap surfaces. Let's go fast and finish this thing. So first we talk about closed trap surfaces. Remember what we talked about in the black hole case, in the Schwarzschild case. You had space and time, and you had matter which was collapsing over here. And as a result of that, at some point or the other, the black hole will form. This is the AKR sort of singularity thing. And then you have an event horizon. What actually happens, if you look at what happens to the light cones, you might ask. So at every point that I can consider over here, suppose I consider a point of this A, B, C. So B, C. As I come closer and closer, the light cone slowly starts to tip towards, and the event horizon turns out to be the exact point where both of the entire light cone now points inwards, meaning that at this point the entire future possibility is inwards. There is nothing that can come out. There is no possibility of it coming out. So escape is not part of the future, literally and figuratively. So it has to go to the singularity. There is no way. And this is the first sort of how should I say, picture, and this is the sort of the picture that Penrose generalized by introducing closed trap surfaces. So basically said a closed trap surface is a surface where all the light rays coming out of it point inwards. So all the future light cones are pointing inwards. So these are all future light cones, and they can be extended effectively to come to a point. And the idea over here is that suppose if you have a stationary spacetime, suppose you had a ring, and this was giving out light in different directions. So you have, so the same thing at a different point of time now, so later on in time. So the thing which was moving inwards, it creates a circle inwards. Thing moving outwards creates a circle outwards. So effectively, the entire light cone, there is some area of the light cone which is outside of the area actually grows. So this dotted line is the area of the initial one, A0. The area in the second one is actually greater than A0. In this case, in a contracting space-time, which is what we are seeing over here, things are contracting. Even if it still gives out two light rays like that in two different directions, but since the space is contracting even more, even after it actually expands by some amount, even the largest thing that could have come about the blue curve is even within the area A0. So by area, I mean volume or whatever hypersurface volume that you have over here. So A less than A0. So this is what it means to have a closed trap surface. If this scenario happens, then you have a closed trap surface colloquially per se. So you have that, and then you have something called geodesic incompleteness. What you require is essentially the fact that you have something called a Cauchy surface, which basically means that there is some surface on which every direction matches and every direction has an initial condition. What this essentially means that there is a maximal causal path, meaning that every point in then space-time is connected by some path with a minimal distance. There is an idea of a minimal distance. So what Penrose effectively proved is that he showed that there is a contradiction. So suppose there is A on which my contraction is initially negative, and I look at some point B, which is the focal point. I can take two paths, say path 1 and path 2. Along path 1, along path 1, the distance along path 1 and the distance along path 2 is the same. Suppose it's the maximal surface. Now suppose the path 1, I can say, suppose push to a point even beyond B, so point P. And then since A to B is minimal, and this is the same geodesic which is actually going from A to B and onwards to P, ABP is also something minimal. So ABP is minimum distance. And since AB along the green one and AB along the blue one are the same, so AB2, by 2 I mean I go along the blue, is like that. So these two are the same. These two are equal. And they are minimal. But if you actually, so suppose now Penrose says, look, okay, but then if I want to go from this point, I could just take a situation where I smoothen out this kink that I have formed. So over here, the path comes up to here and then goes in this direction. So there is a kink at this point. Instead of that, I could have, instead of going like this, I could have gone something directly like that, and that would have minimized my path length. So I could, so if I went along AQP, that would be smaller than AB2P. But then this is a contradiction, because if I had assumed right at the start that, look, okay, everything was minimal and things were like that, I end up with a contradiction. And as a result of that, there are multiple things that we have assumed, and the conjugation of all of those things, there has to be a fallacy somewhere. Has to be an incompatibility somewhere. The thing that people understand over here is the fact that this thing that we had done is taken up to the focal point and extended beyond the focal point. That is not possible, which essentially means that I can take a curve like that and I cannot extend it beyond focal points, meaning that I cannot extend it beyond certain points. So there is a region in space-time where I have to stop, meaning that the geodesic that I was considering is actually incomplete. It cannot be stretched to arbitrary times like I was doing before. And this is the proof that Penrose gave of incompleteness. Remember, he defined singularities to be like this. And this is what people understand to be the general, one of the general ways of defining singularities. And he proved that, look, there is a logical fallacy. There's some contradiction happening if you want all of these things happening at the same time. So there has to be a singularity. And we can look at Penrose's PRL article, which does exactly the same. As you can see, he's looking at little light cones over here. And at the event horizon, the light cones are always inside. They're always inside and whatnot. So this S2 or T2 in this case is the trapped surface. And once it has hit a trapped surface, a closed trapped surface, it has to go to a singularity. There must be a singularity at some point. And so these are the actual words that Penrose used. So it will be shown here in the outline that 1 to 5, these conditions are together inconsistent, and hence there must be a singularity. The geodesics are incomplete. So what I should say after this, that this is basically geodesic incompleteness. And what Penrose's article basically shows is that this is general. As long as you have a Cauchy hypersurface, which is a place where you can give initial conditions to each world line, they will always, and if there is a trapped surface which is formed at any point, they will always lead to a singularity, no matter what you do. So beyond the trapped surface, even if it's not spherically symmetric, it's this, it's that, whatever, nothing can stop singularities. It will always happen. So this is the main contribution of Penrose. Of course, this got extended later on by Hawking to cosmological singularities and a whole slew of this kind of research, which all basically show geodesic incompleteness or work with geodesic incompleteness. So you can say Penrose birthed this entire field, at least the direction that it's on. It was started by Penrose. So the main takeaway, now I'm at the end of my talk, the main takeaway is that singularities are not singular in nature. They're everywhere, and they are robust predictions, as the Nobel citation says. They are robust predictions of the general theory of relativity. Of course, you might ask, okay, what happens over here? But then we'll take it up later. So that's all. Thank you for your attention, and I'm sorry I took longer than I budgeted for.
Okay, thank you so much. Thank you. I mean, this was fantastic. I mean, I have not heard a compressed introduction to something as difficult as general theory of relativity and black holes. But at least I think the big picture hopefully would be clear even to people who do not have the mathematical background to follow everything that you said. I think this is brilliant. I know you've taken a lot of questions during the talk, but there are actually many other questions. And
sure, please. I'll be
you're okay with taking a few more. So let's go to Facebook, and actually Harsh is asking, he's still not clear with space-time graphs. Can you explain space-time graphs once more?
Sure.
Beginning, because I think that's pretty much basic to understanding anything that we've been doing.
Yeah. So let me actually open up space-time graph. Right. So you want to go to space-time curves, right? Okay.
Yeah, I think this is it.
Right. So what you're doing is, suppose, let me see whether I'm a good enough artist. What you're trying to do is, suppose you're looking at a picture, as I said. You have, say, I don't know, a car, right? And the car is moving in this direction. So at time equal to 1, the car is here. Time equal to 2, car is somewhere over there. Time equal to 3, car is somewhere over there, right? So what would you get if you actually superimposed these pictures together? If you just put all of the time values together on top of each other, you would get basically a hypothetical car at this position. You'd get a hypothetical car at this position. But I'm not asking you to do that. What I'm asking you to do is shift the second curve by 1 unit up top. So this one, which is the second one, so this is car at position 2, this is car at position 3. So if I had just superimposed images, I would have gotten this. What I'm asking you is not to do that. I'm asking you, since it's at time equal to 2, shift it upwards, shift the second image upwards by 1 unit. So hypothetical car number 2, my cars are getting more beautiful by the time. And at time equal to 3, since it's 2 units of time difference, you move it up by 2 units. So if this is the first unit, you move it over here at the third unit. So car number 3 is over here. So now if I join the trajectory of where these points are going to be, I get something like a straight line, right? I could have looked at 1.5 and it would be somewhere in between 1 and 5, somewhere over here. Somewhere over here would be 2.5. So this is how you construct space-time. Now I have space in this direction, and this is time in this direction, right? And this is what they're talking about over here, that you take snapshots of space, you displace them along the time axis, you stack them in order, and that creates sort of shapes in space-time. And that's how you get space-time diagrams. If the car was just stationary, think about it, then it would just be at the same place at every point of time. Whatever.
Okay, great. And so what, these light cones were sort of tilting at the end, etc. So are all light cones aligned in a particular direction, or what defines how are light cones aligned?
Right. So effectively, okay, there is no easy way of answering this, because the orientation of light cones. Okay, let me start from the start in one place. Just give me a little bit of time. Right. So let me start from here. So Einstein's GTR basically gives me equations where this mu and nu were coordinates, indices of the coordinates. So here x0 effectively is time, x1 is x, x2 is y, and x3 is z. This is how I introduced the thing to you. But the beauty of Einstein's GTR is that you could choose any coordinates that you would like. Like I showed you in the metric is the same. All you care about is the actual metric. Whether you express it in terms of xyz or r theta phi, it doesn't matter. So in the pictures that I showed you afterwards, over here, these coordinates, these are light cones that you find in terms of some particular coordinates called Edelstein, Finkelstein, and Edel something, I forgot the name, coordinates, but you can find this in any GR book if you like, or a simple Wikipedia search will also satisfy you, I guess. Over there, what you find is the null vectors, the null killing vector fields, and then you find how these things are oriented. So if you look at Penrose's original diagram, you find these coordinates of v equal to constant, and you find coordinates of u equal to constant. And u and v are these Finkelstein coordinates that you were talking about. The points at where these two things intersect is what defines the orientation of your light cone. Think about what happens on a sphere. You would have, say, you have longitudes, and then you have you have latitudes, and then you have longitudes, like that. So what is the local angle? It's at the points where, so at this point, the light cone is oriented in this way on the surface of the earth. I mean, it's a bad example, but whatever. So you have two directions over here, two geodesics, and then they define the orientation of the light. So the geodesics actually bend. The light cones help you trace how the geodesics bend. So I hope that answers your question.
Okay, and okay, I think that are actually just way too many questions, but
either I did a good job or a pretty
no, you
bad
did a
job.
very good job, and I think what you can do is maybe we can look at it and we'll put up the answers. I've saved the chat so we can put up the answers later on.
Sure.
So does it mean that there are light cones where the past cone overlaps the future cone because light coming from inside can only go back in? Does that question make sense? I don't know.
No, I mean, so remember, if I am at a certain, light cones are local to a point. So if I were to go back to Scott, if I were to go back to this picture, if I were to think of a point over here, then it has a future, and a point over here has a different future. So the future of this point can have some overlap with the past of the next subsequent point. So that's how it's sort of like a relay race, where I'm at a point, I can only hand it to the person in front of me, who is to the future of me. and the person who's in front can only get things from behind, which is the past. So there's a relay race of the particle happening in whatever, in this sense, that the future of one goes with the past of the other. So it's not like light is actually going outwards or coming back or something. It has no other way to go out. It can only go for a set course towards the singularity. There's no other way. So that is what Penrose is showing over here, or the simplified picture if you want, which shows that once you have a closed trap surface like this, all light can actually go towards. You see, at this point, the entire light cone, the entire future is towards the singularity, right? This entire cone is just looking at the singularity. There's no way that it's looking at somewhere outside. So whatever light is coming in, if this point has to contact this point, there can be a light which goes here and then all the way down into the singularity. So this is what is happening. Future of one overlaps past of another, not future of one overlapping with past of the same. That doesn't happen ever.
Okay, so I think it's coming up to 12:30. We should probably take a break here. Saranyo, we will take questions over email if there are some interesting ones, and maybe you can put a summary sometime. Yes, sure. Thank you for putting this up. I would like to remind our viewers that we are not done with the physics prizes yet. The physics prize was given in two parts. Penrose was only the first part. There's an equally exciting thing and very, very exciting experiments that actually showed that there is a black hole in the center of our own galaxy, the Milky Way. Lankeshwar will be telling us about that 2 weeks from now on the work of Gensel and Hess. But before that, next Sunday, we're going to be looking at the chemistry prize, where Tuli and Mahima will look at the technique of CRISPR and how that has really made advances in genome editing possible, which were just which are unbelievable. I mean, the power that it has. So CRISPR coming up next week, followed by the black hole, back to physics, the black hole in the center of the Milky Way. And yes, thank you for joining us at Chai and Wai on Diwali Day. This is probably the third time in the last 12 years that we've had a Chai and Wai exactly on Diwali or so. And typically it's always been fireworks. It's always been the signs of fireworks. This time we decided to go to the dark side for a change. Diwali is on an Amavasya night. It's on new moon night, the dark side. And we talked about black holes.
Interestingly enough, when you go to at a point where things are so dense and so everything, the black hole itself can turn up its own fireworks, which are called quasars and whatnot. And there turns out they're the brightest things that you can find in the cosmos. So we're not too far off from the theme per se, but that is a regime for another talk or another course by itself.
Absolutely. And till then, please stay safe, have a happy Diwali and a happy festive season, and wear your mask if you're going outside, of course. And again, Saranyo, thank you so much for doing this. It's been
thanks, Arnav, for having me.
And all of you, thanks a lot, and keep watching Chai and Wai.
Okay. Thank you. Bye.